Dear guys, welcome to my YouTube channel. Now, yesterday I did few numericals based on Carnot engine, okay, and on previous day I did it for first law of thermodynamics. So let us do few other numericals for heat engine, or you can say for Carnot engine. So let us do few other numericals. So the first numerical of today is that this is a Carnot diagram. Say this is a Carnot cycle, that is PV diagram, and this is the picture. Say this is a picture. The Carnot cycle is a rectangle. Okay, the Carnot cycle is rectangle. Here given that when a system is taken from the state A to state B along the path ACB, 80 joule of heat flows into the system. Okay, that is when the system moves from ACB, 80 joules. Okay, so this is 80 joule. Okay, and the system does 30 joules of work. Okay, so here given the work is 30 joule, that is along this path. Okay, so here we have to find out how much heat flows into the system along the path ADB if the work done is 10 joule. Okay, we have to find out how much amount of heat flows into the system along the path ADB. That means along this path. Okay, so at first we have to find out the change in internal energy. Now what should be the from the first law of thermodynamics? Change in internal energy plus work done. Okay, and here we take this as positive. Okay, that means QACB, this is 80 and this is UB minus UA and this is 30. So what we get, UB minus UA, that is the change in internal energy, is 50 unit. Okay, 50 joule. Okay, now the question is that how much heat flows into the system along the path ADB if the work done is 10 joule. Okay, so we have to find out the heat flows into the system along ADB path. Okay, along this. What is given here? The given W is 10 joule. Okay, W is given 10 joule. Okay, here we take, if the system moves from A to B, we take it positive, and when it is returned from B to A, we take all the quantities negative. So here we have to find out how much amount of heat will flows into the system when the when the system moves along ADB path. So what will be my QADB? That is, ADB path means the particle moves from A to B via ADB path. That means here also we take all the quantities positive. So this will be my UB minus UA plus W. And what will be my UB minus UA? That is 50. And what is W? That is 10, 60 joule. Okay. So this is the work done in moving from A to B via the path ADB. So at first you have to find out the change in internal energy. Okay, change in internal energy, and at first they are given QACB is given and W is given. So from first law you can determine the change in internal energy, and then also you move from A to B but along the path ADB. So what will be the heat? The change in internal energy plus W is given 10 joule, and you find out the change in internal energy 50. So this is the result, 60 joule. So this is also a simple diagram. Now what we consider here, conventionally we take that when the system moves from initial state to final state, we take all the quantities positive, but when the system returns from that, we take all the quantities negative. Okay, so this is the simple case. Okay, so this is the first numerical. Okay, now let us move to the second numerical. Now we do another part of the same question so that you can adjust, you can understand the reverse process also. Okay, we will do the reverse process. Okay, so the another problem is that the system is returned from B to A. Now the system is returned from B to A along the curved path, that is this path. Okay, fine. uh, the work done on the system is 20 joule. Does the system absorb or liberate heat, and how much? Okay, so since the system is now returned from, when the system returns from B to A via curved path, this is 2 but same picture, curved path, work is done on the system is 20 joule. Work is done on the system, that means we take minus. Okay, because previously I told that when work is done on the system we take it positive, and when work is done on the system we take it negative. Okay, so here W is negative, and we have to find out does the system absorbs or liberate heat and how much. Okay, so for the curved part from B to A, we can write what? Q will be, that is same, UB minus UA plus W, but here the system returns from B to A, that means we take internal energy also negative. Previously we found the internal energy 50 joule, here we take minus 50, and W is minus 20. Again I say I use the minus sign because work is done on the system, that's why I take the work negative, and I take the internal energy negative, because since the system is returning from B to A and work is done on the system. So you have to remember this thing, that when work is done on a system this is positive, and when work is done on a system this is negative. So negative sign indicates that heat is liberated so by the system. Okay, so this negative sign indicates that, minus sign indicates that heat is liberated. Okay, heat is liberated. We always have to use this sign convention. Okay, must remember this. So let us move to another numerical. So let us move to another numerical. So calculate the work done, find the work done when 1 mole of ideal gas expands isothermally. When 1 mole ideal gas expands isothermally at 27 degrees Celsius. Okay, so we all know the formula. This is easy. For isothermal expansion, what would be the formula? nRT ln V2 upon V1. Okay, expands isothermally to double its volume. That means if V1 is V, we take V2 equals to 2V. So what? N is given 1 mole. R you take in SI unit, that is 8.314 mole Kelvin. joule per mole Kelvin. T is what? 27 degrees Celsius, 300 Kelvin. And this is ln V2 by V1, 2V by V. Okay. So this is 1 multiplied by 8.314 multiplied by 300, and we all know the value of ln2. ln2 is what? 0.693. Okay. ln2 is something that is 0.693. So if you do it in calculator, okay, so the result will be this joule. So this is the answer. But if there is a minus sign, if here given that compression, then this term will be lesser than this term, and automatically a minus sign comes. If it is compressed, then this term is small and this term is large, so as a result automatically a minus sign comes, and that minus sign is nothing but clearly indicates that work is done on the system or the gas is compressed. Okay, so this is also easy. Now another numerical, that is given that a Carnot engine has a efficiency 30%. Find, that is given 30%. That means 0.3. Okay. So when the sink temperature is 27 degree, 27 degree means 300 Kelvin. Okay. So you can easily find the source temperature at first. Then so you can easily find out the source temperature. So this is 0.3, and this is what? 1 minus 300 by T1. So this is what? 300 upon T1, 1 minus. So this is what? T1 will be this, and if you do it, 428.5 Kelvin. So we can easily find the source temperature. Now let's see what it tells. What must be the change in temperature of the source to make its efficiency 50%? Okay, what must be the change in temperature of the source to make the efficiency 50%? So the initial source temperature is this, we write T1. Okay, now the second condition says now the efficiency is 50%. Now say we can say it eta dash, that is 50%, that means half, and sink temperature remains same, and that is 300 Kelvin. Now you can find out the source temperatures. Say eta dash, this is equal to 1 minus, say this is T1 dash, and T2 remains same. So what will be eta dash? That is half. So 1 minus T1 dash upon this. So what? T1 dash by 300, this equals to half. So T1 dash, sorry, sorry, I write down the formula wrong, extremely sorry. Eta dash, that means half, this equals to 1 minus sink temperature by source temperature, that is that. Okay, so 300 by T1 dash, this is equals to half, and my new T1 dash will be 600 Kelvin. So you will get the source temperature both the cases. So what will be the change in temperature? If you call it delta T, so T1 dash minus T1, this means 600 minus 428.5 Kelvin. Okay, so this is 171.45 Kelvin. So this is the result. Okay, so these are the few numericals that I did. Now okay, few are the numericals. Now I already told, let us do another work, another numerical. So here given a Carnot engine absorbs 10 to the power 4 calorie of heat. That means Q1 is 10 to the power 4 calorie unit. Fine. At a reservoir of 627 degrees Celsius. This is in degrees Celsius. Kindly ignore the sound which is coming from outside. This is 900 Kelvin and rejects heat to sink at 27 degrees Celsius. That means 300 Kelvin. Okay, so we have to find out the how much work does it perform. Okay, how much work it performs. So we have to find out the efficiency 1 minus T2 by T1. So this is 600 by, this is 2 by 3. So this is the efficiency. So the efficiency is 2 by 3. Now how much work does it perform? We all know the formula. We all know the work formula, that is eta. This is equals to W upon Q1. So what will be my W? That is eta into Q1. What will be eta? That is 2 by 3 and Q1 is 10 to the power 4. Okay. Okay. So this is in so this is the W. So since the unit is calorie, I can write here calorie, but if you convert into joule, no problem. Just 2.3 into 1 calorie means 4.2 joule. So multiplied by 4.2, this is the result in joule. You do it in calculator, but if you do up to this, it will also fine. Since the unit is calorie, here I write calorie, but if you convert it to joule, 1 calorie equals to 4.2 joule. So multiply this by 4.2 and the answer will be in joule. So if you do it in calculator, so what will be the result? Well, 2.8 into 10 to the power 4 joule. Okay, fine. So this is all for today. Now dear guys, I covered all the numericals of first and second law. Now few numericals remain regarding the entropy chapter, that I will do in next day. Okay, but very soon I have to start the fourth chapter, which is very important, that is Maxwell's thermodynamical relations. Okay, so that chapter is entirely based on mathematics, that is differential calculus. So in from our next class I will start that chapter, and I will also do the numericals regarding entropy. Okay, thank you.